Hi, this is Mrs. Blake, and today we're going to talk about the combined gas law. In order to watch this video, you might want to have a calculator and piece of scratch paper ready so that you can try some of the problems. So, there are four main variables used when we talk about gas laws. Those four main variables, one of those variables is going to be pressure. Pressure is going to be abbreviated with a P, and pressure is the amount of force per unit area. Pressure can push a gas particles closer together or can let them spread further apart. Gas also puts a pressure on the outside, so pressure is measured that way as well. Units for pressure. Units for pressure can be measured in atmospheres, which is ATM. Units for pressure can also be measured in kilopascals, which is kPa. Pressure can be measured in millimeters of mercury, or in the US system, inches of mercury. Pressure can be measured in torr, and you also may run into pressure as PSI, which is the amount of pounds per square inch. The good thing about pressure is that with the combined gas law, as long as the unit is the same, you don't have to have one specific unit. So if both your units are in atmospheres, you're fine. If both your units are in kilopascals or millimeters of mercury, you're okay. It's only when those units are different from one another that you have to do some converting. Second variable, an important part of gas laws is going to be temperature, and temperature is going to be abbreviated with a capital T. Temperature is the average amount of kinetic energy an object has, and it's the measured amount of energy that a gas particle has. Temperature is the one unit in gas laws that must be unit specific. Temperature must be in Kelvin when dealing with gas laws. Now there's a conversion factor. If you have degrees Celsius and you add 273, you get it to Kelvin. But you cannot use Celsius or Fahrenheit in any of your gas law calculations. The third variable that is common in gas law problems is V, which is going to refer to as volume. It's the amount of space an object takes up. But since gas is spread out to fill the entire volume of the container, whatever the size of the container is considered to be the volume of the gas. Again, you can run into multiple units with volume. You can run into milliliters. You can run into liters because volume is sometimes measured as a liquid or a fluid, but then you can also measure it as centimeters cubed or meters cubed. Again, just like with pressure, as long as my units are the same, I don't have to have one specific unit to be calculating. The only unit I have to worry about a specific unit is Kelvin, and that's for temperature. The last variable that you run into with gas laws is going to be the amount of gas, referred to as an N, and that's known as the moles of gas. And it's how many atoms or molecules of gas there are. This is held constant in Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. So the only time you really have to worry about using the number of moles of gas is going to be in the ideal gas law. And since we're using N as moles of gas, the unit then for this would be moles. So when we take a look at the combined gas law is made up of three additional gas laws. Boyle's law is going to compare pressure and volume with a constant temperature. Charles' law compares volume and temperature with a constant pressure, and Gay-Lussac's law compares temperature and pressure with a constant volume. But those two variables can all be combined into one that we refer to as the combined gas law. And the combined gas law takes a look at the variables pressure, volume, temperature, all as part of the same calculation. So putting all of these equations together, we end up with P1V1 over T1 is equal to P2V2 over T2. But the cool thing about the combined gas law is it has the rest of the gas laws inside. So if I'm using the combined gas law and they tell me my temperature is held constant, that means that I have P1V1 is equal to P2V2, which makes it the same as Boyle's law. And if I am going to hold my volume constant, I get rid of that, and P1 over T1 is equal to P2 over T2, and I end up with Gay-Lussac's law. So while the combined gas law is one type of calculation, combined gas law can actually be used for all four types of calculations. So let's take a look at some of the calculations that go with gas laws. And the first thing you're going to notice in a gas law problem is there's going to be lots of numbers. So if we're taking a look at a gas law problem, some magic words, of and at, because at is going to tie this number together, and of is also going to make those part of an initial amount or initial set of numbers. So that when I'm reading a problem, a 280 milliliter sample of neon exerts a pressure of 660 torr at 26 degrees. These numbers are all going to be related to one another. And as I keep reading, at what temperature, so that's what I'm trying to find is a temperature, would it exert a pressure of 940 torr in a volume of 440 milliliters? Those become the second set of information that I have. Well, if I've got pressure and I've got a volume and I've got a temperature, this is going to be my combined gas law. So I have P1V1 over T1 is equal to P2 V2 over T2. And if you want to take a look at this, I find that students have a lot of difficulty solving for temperature on the bottom. But if you want to look back at math and you cross multiplied, I can take my temperature 1 and put it over here, and I can cross multiply and put my temperature 2 over here. So the formula I'm really going to use for this puts T2 with P1V1, and that's going to be equal to P2 V2 with T1. And that just makes it a little bit easier to solve when we talk about the calculations. So I have 280 milliliters. And 280 milliliters is going to be my initial, that would be 1, my initial volume. So I am going to take that 280 milliliters and put it here. And I have a pressure of 660 torr. So that's my initial pressure. And I have temperature, but on this side of the equation, I'm looking for temperature 2. Well, that's actually what I'm trying to solve for in this equation. So I have a pressure of 940 torr is a new pressure. And I have a volume of 440 milliliters. And this is where my temperature 1 goes in. But it's really important to remember that even though they give me the temperature in degrees Celsius, temperature must be in Kelvin. So to turn the temperature in Celsius into Kelvin, Kelvin is going to be equal to my temperature plus 273. So I'm going to take this 26.0 degrees Celsius and I'm going to add 273 to it, and I'm going to come up with 299 Kelvin. Kelvin is not a degree. So on this side of the equation where T1 goes, this is going to be 299 Kelvin. Again, you need to be really careful that your temperature 1 goes on the opposite side of your pressure 1 and volume 1, and your temperature 2 goes on the side with your pressure 1 and volume 1. So if I'm calculating this out, my unknown is on this side. So I can divide both sides by 660. And I can divide both sides by 280. And I am going to take 940 times 440 times 299. I'm going to divide that by 660. And I'm going to divide that by 280. And I am going to come out with a temperature equal to 669. But in a gas law problem, this is in Kelvin. And I need to be careful because my temperature does not want my temperature in Kelvin. It wants it in degrees Celsius, so I need to subtract that 273 from that. And to get my answer in Celsius, like the problem is asking, I'm going to subtract 273, and I'm going to come up with 296 degrees Celsius. Sorry, 396 degrees Celsius. So let's take a look at another example. A sample of gas has a volume of 4.20 liters at a temperature of 60 degrees Celsius and 1 atmosphere of pressure. So again, when I am looking at this equation and it's P1 V1 over T1 is equal to P2 V2 over T2. Again, I like to flatten this equation out. It makes it easier to be able to solve the algebra. So I have T2, which is something I'm going to have to come up with. I have a pressure 1, a volume 1. I have a pressure 2 and a volume 2, and that's where my T1 is going to go. So I've got a volume, and that volume is going to be 4.20 liters. I have a pressure, and they tell me the pressure is going to be in 1 atmosphere. Again, my units for pressure don't matter as long as the units for pressure match. Same for my units of volume. So as long as this is in atmospheres, and I am trying to find pressure here, and as long as my volume is in liters, and this is in liters, I don't have to worry about what those units actually are. So I have a temperature 1, but again with temperature, I have to take that 60 and I have to add 273 Kelvin to it. So my temperature 1, which goes on the opposite side, is going to be 333 Kelvin. So I am supposed to calculate the pressure if the volume is changed to 5 liters and the temperature to 27 degrees Celsius. So my pressure 2 is what I'm trying to find. My volume 2 is going to be 5.00 liters. And my temperature 2, and again that goes on the initial side, is going to be 27 degrees Celsius, but I have to take that 27 degrees Celsius and add 273 to it. So I'm going to come out with 300 Kelvin. So my unknown is going to be on this side here. I'm trying to solve for pressure. I'm going to divide both sides by the 5.00 liters. So that liters can cancel out, and I'm going to divide by the 333 Kelvin. So that cancels out. And I'm going to punch those numbers into my calculator, and I'm going to come out with a pressure that is going to be equal to 0.76. And since the original pressure was in atmospheres, this is also going to be in atmospheres. So let's try one more calculation quick. A weather balloon is filled with a volume of 150 liters on a day when the temperature is 10 degrees Celsius. If no gas escapes, what would be the volume of the weather balloon after it rises up to an altitude where the temperature is -8 degrees Celsius? Now, again, and I'm just going to use the flattened formula, T2 is P1V1 is equal to P2V2 over T1. But this time they don't tell me anything about pressure. And if they don't tell me anything about pressure, I can get rid of pressure from my combined gas law, and really this is going to be a Charles law equation. So my original volume is going to be 150.0 liters. My original temperature is going to go on the opposite side, and it is going to be 10 degrees Celsius, so I add 273, and I'm going to come up with 283 Kelvin. My new volume is what I am trying to find, and I have an original temperature of -8, which if I add 273 is going to come up with 265 Kelvin. So I'm going to divide both sides by 283. And I'm going to calculate this out, and in my calculator I am going to come up with a volume equal to 140 liters. So when you're taking a look at gas law problems, be very unit aware. Have a great